Hello, everyone, and welcome to today's ACM Learning webinar. This webcast is part of ACM's commitment to lifelong learning and serving the over 97,000 computing professionals and students who are ACM members. My name is Worley. I'm the founder and CEO of StrangeWorks and a serial entrepreneur. And you can find more about my info and background in the bio widget on your screen. So we want to start today with a little bit of ACM highlights. For those of you who may not be familiar, who may be unfamiliar with ACM, and what it has to offer, here's some more information. ACM offers educational and professional development resources that bolster the skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org, and you can see some of the highlights on your screen now. ACM recognizes the role of computing in driving and innovations that sustain competitiveness in a global environment. ACM provides timely computing information published by ACM, including the communications of the ACM and Q magazines, access to the ACM Digital Library, the world's most comprehensive database of computing literature, international conferences that draw leading experts on a broad spectrum of computing topics, and support in education and research, including curriculum development, teacher training, and the ACM Turing and ACM Prize in Computing Awards. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you'll find a number of additional widgets and resources. You can download a copy of the slides from the Resources window. If you're experiencing problems with the slides or audio, press the F5 key in Windows, Command+R if you're on a Mac, or refresh your browser on your mobile device. Or you can close and relaunch the presentation at any time. To control the volume, adjust the master volume on your computer. If you have questions during this webinar, please make sure to type them into the Q&A box at any time during the webinar and click the Submit button. I'll be organizing your questions and giving them to Jay after he's done with this presentation. As Jay speaks, he'll reserve time at the end for those questions. So again, if you type them in there, we will see them and we'll make sure that we try to get them asked. This session is being recorded and will be archived. You'll receive an automatic email notification when it becomes available, and check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey. Please take a moment to open it on your screen. Take a minute, fill it out, help us improve the webinars. And you may also open the link at the survey at any time from the resources window on your screen if for some reason you need to leave early or whatever. We would really appreciate that feedback. Now, you can also use Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as your tweets, comments, and questions using the hashtag #ACMLearning. We would really appreciate it if you would share that on social media and help us get more interest in this presentation. We'll be watching for your tweets. We also have a new community discourse page to continue the discussion after the webcast, including questions that we don't get to during the Q&A session. Today's presentation is QISKit, a Swiss Army knife for quantum computing by Jay Gambetta. Jay Gambetta is a quantum information scientist researching in the field of quantum information and computation. He joined IBM in 2011 and is now the manager of the Quantum Theory, Software, and Applications Group. At IBM, he has contributed to work on quantum validation techniques such as randomized benchmarking and gate set terminology, quantum codes, improved gates and coherence, near-term applications of quantum computing, the IBM Quantum Experience, and today's subject of our presentation, QISKit. Prior to IBM, he held positions as the Institute for Quantum Computing in Canada and was a Post-Doctoral Fellow at Yale University. In 2014, he was named a Fellow of the American Physical Society, nominated by the Topological Group for Quantum Information. He holds a doctorate in physics from Griffith University Australia and has over 90 publications with more than 10,000 citations in the field of quantum information science. Jay was also a member on the panel of Quantum Computing Far Away, Around the Corner, or maybe both at the same time, at the 50 Years of ACM AM Turing Award celebration in 2017. So without further ado, Jay, take it away.
Thanks, Worley, for the introduction, and thanks ACM for inviting me to give this talk. To be honest, I've never done a webinar before, so let's see how it goes, but I'd like to tell you about the work that we're doing at IBM, and in particular the QISKit. So basically, quantum experiments are getting way too complicated to control by hand. Here's a photo of one of my colleagues, Antonio Kokolis, looking confused as he tries to work out what to do with an experiment. So as these experiments get bigger and more complicated, we need to build better tools for enabling this. And this is basically the goal of QISKit. It's to provide an open source platform for building quantum programs that we can keep changing with our hardware. And to be exact, it's an open source development kit for writing quantum computing experiments, programs, and applications. We've put it on Git. You'll see that there are many parts to QISKit. There's an SDK, which I'll spend a lot of time later talking about, which is the SDK in Python. There's a tutorial, which is a collection of notebooks and examples of how to use it. There's OpenQASM, which is a specification for what to do with quantum circuits, which I'll touch on. And there's more information about different backends and user guides that you can use. If you're interested and have Git, I recommend that you go to our page and either follow us or keep updated. We pretty have an aggressive loop of updating this. We just updated to 0.4 on Monday, and we're working towards really pushing this further. If you see issues, please add them. We've got pull requests for fixes. We'd be happy to discuss them. And this is really a community effort. We're really engaging with myself being a quantum information scientist, and a number of developers, and anyone that wants to program a quantum computer to see how this is done. We've also put together a website. This website just is like very simple at the moment. It gives you the latest version. It gives you quick links to access the tutorials, the documentation, and it gives you a link for joining our Slack community where we are discussing very actively the directions for future updates. What are the next features we want to do? And in particular, this one was to get the release 0.4 out, which I just said came out on Monday. So that's enough of the advertisement section of my talk. Let's get down to the details that I'm going to talk about. I'm going to break my talk into 3 parts. Obviously, the first part, quantum computing, is very exciting. It definitely has, for someone in the field, it's definitely entered a phase where it's gone into the media and reached out beyond my community. So I'm going to try and give you a very high-level overview of why it's exciting. I'm going to give you a quick overview of what a quantum computer looks like today, and then I'm going to go through our QISKit stuff. So what happened? Well, for a very long time, people were doing quantum information scientists and experimentalists were focusing on single qubit experiments, right? And 2-qubit experiments and small experiments where the goal was really to improve how long the system behaved quantum mechanically. And then a lot of theoretical work was trying to understand the large N limit, or the limit with perfect qubits, of what these could be do. And recently, ourselves included and many other groups, we've started to see this change where we're going from a point in time where the experiments are starting to get more complicated than we can actually start to simulate. So I like to say we're transitioning from this sort of quantum science regime to this quantum ready regime. And we're going to work towards working out what quantum can do. It doesn't necessarily mean in the next couple of years you're going to see quantum is better than classical, but working out how to control these systems and eventually getting to this quantum advantage stage later on in some point in time. So I think we're really going through this phase change where we're coming from science to this quantum ready. But saying that, experiments still look very much like a lab. Here's a picture of one of our experiments. The silver thing in the middle is the cryogenic fridge where the qubits are cooled down to, and it very much looks like a lab. So why are people excited? Well, many people say that quantum computing falsely is like the next step in Moore's law. And we've seen a lot of growth and innovation in classical computing. There's been tremendous, and there will continue to be tremendous amounts of revolution where we work out how to do better things. But don't think of quantum computing as the next step on this. This will continue and process information in the classical sense the way it does. Quantum computing is basically a new model of computation. So you've got to think of it completely different. And when I try and start and explain what's different about it, you find yourself explaining exponentials. And anytime I find myself explaining an exponential, I like to refer back to this famous little little story. Basically, the story is the person that invented chess went to India and talked to the emperor and showed the emperor. And the emperor was so impressed, and he asked for a wish. And the guy said, basically, on the first day, just give me 1 grain of rice. And on the second day, 2 grains of rice, and so on until all 64 squares were consumed. The emperor thought the man was crazy, and he agreed to the reward. And as expected, on the first day, it's very simple. It's just 1 grain of rice, okay? Nothing special. On the second day, it's 120 grains of rice. This is probably about 2 spoons of rice. By a month into it, it's probably more rice than anyone would ever eat in their lifetime. And then by the end of the chessboard, it's more rice than would fill Mount Everest. So exponentials, it's really hard for us, because we don't experience them in every day, to appreciate how fast they grow. And the same type of exponential is also present in many problems. For instance, there is many problems that are just intractable because to search for the solution, the best known algorithms at the moment have a runtime that scales exponentially with the input size. And we believe pretty strongly, even though it's still a conjecture, that there are problems that are hard and there are problems that are easy. And I would allow someone else to go into details of this a lot more because I don't want to spend too much time on this, except just to say quantum computing is the only new novel hardware which changes the game. And this is one of the things that makes it exciting. We don't know how it will solve all these hard problems. We only know a subset of problems that it has a way to look at. But because it changes this game, it's worth the investigation to work out why it's different. Okay, so I said it's a new model of computation. I'm probably pretty sure that many people out there have heard that it's because it does everything at once. I really, really dislike this description of quantum. And so working with Charlie Bennett, who's a fellow at IBM, when we first put some of our devices online, we tried to think what was exactly different. And I think the best way to say is it comes down to 2 different concepts that you just have to accept. And the first one, it seems really easy. A physical system in a perfectly definite state can still behave randomly. Okay? That is just, you're going to have to accept that about this system. And the second is that 2 systems that are too far apart to influence each other can nevertheless behave in ways, though individually random, are somehow strongly correlated. So what do they mean? Well, I put this little toy game together and to demonstrate it. So on this slide, you'll see we have a qubit, which we denote with this Q, prepared in the 0 state. We have this operation which we call a H, which is known as a Hadamard. Basically, you can think of this as a quantum coin flipping operation. So in this experiment, you start in a qubit in a well-known state 0, and you flip it, okay? And then you measure it, okay? And the outcome, as expected, comes out 50% in the 0 and 50% in the 1. So if I was to ask, what would happen if you did this coin flip twice? What would many people expect? Worley, what would you expect if you flipped this coin twice? All right. Since Worley didn't hear, let's
twice. I'd expect to see some random probability that I would get a heads or a tails, and I would probably think that I wouldn't get the same one twice, just because that's me.
Yes, and that's precisely right. That's our classical intuition. We expect if it was truly flipping a coin, you would expect to see the outcome. You would expect when you histogrammed it to get the same 50-50. And what you find quantum mechanically, sorry, I'm having trouble holding the phone and hitting go forward on the slide, is with 100% certainty, you always get it in the 0 state. And this is because quantum randomness is not like classical randomness. it depends on how you measure it. In particular, you can think of this final part of this H in measurement as asking a different question in quantum. You're asking the question, are you in a positive superposition or a negative superposition? And when you do that, you're finding out that this quantum system is in this positive superposition. So this quantum randomness is very fundamentally different to our intuition of classical randomness. And as an example, we can continue with entanglement. So in this little experiment, now I've brought in a second qubit that's initially prepared in the H state. And then we have this operation which we call a C0. This C0 does a controlled flip. If the first qubit is in the 0, it flips the second qubit to a 1. Flips it from 0 to 1, okay? And if it's in, I'll restate that. If the first qubit's in a 0, it does nothing. If the first qubit's in a 1, it flips the second qubit from 0 to 1. And this generates entanglement. So here we were asking the question, is the first qubit in a 0 or 1? And we're asking the question, is the first qubit in a superposition, a positive superposition or a negative superposition? And what we find out when we do this is that qubit 1 has no information about the quantum state. It's 50-50 for both this. It's neither in a superposition or it's neither in a 0 or 1. So looking at it individually, we know nothing about the system. And it's not until we start and we come in and we do a measurement that we ask for and look at the correlations. In particular, we can look at the correlations in the computational basis and ask, are you both in 0 or you're both in 1? And we find that if the first one is in 0, the other one is in 0. If the second one is in 1, the other one is in 1. And then if we ask, are you in a positive superposition or a negative superposition? We find in the superposition basis, we see that is perfectly correlated in the positive superposition and negative superposition. So entanglement is something about the whole is bigger than the parts. To be honest, entanglement's a little bit more subtle than I've given in this demonstration because there is still a local hidden variable model that explains this. And for those that are interested, we have a tutorial that goes into the details. But you can think of it as a high level. It's a resource that makes a system in the whole much more powerful than its parts. And how we exploit that is part of what we have to do for quantum computing. Now, to do gates, to do quantum circuits, we continue and we make up these quantum circuits by placing many of these gates together. You just add more and more gates, and you can view this as time goes across from left to right, represents the time of the circuit. From top to bottom represents the number of qubits. And this doesn't give you timing explicitly, but it gives you dependencies. It tells you which gate has to occur. If gates occur at in the same row, it doesn't matter which one of them comes first. Like in this top circuit, it just tells you that the H, the X, the ID gate, the S, and the S dagger must all occur before the C0. And the S must occur after the Z. So it's like it just gives you some dependencies of the circuit, and this represents the operation. So in some sort of math terms, a quantum computation represents applying a big unitary. And the C0 has a matrix representation, as I said before, that flips the qubit depending on whether the controller is in the 0 or the 1. And we can show with arbitrary single qubit rotations, which are given in this matrix, we can generate any unitary. And in particular, with the finite set, we can come up with an approximate solution to any unitary of a given accuracy that allows us to represent a whatever operation we want to do on a quantum computer. So these become the gates. This slide, I give the credit of this slide to Scott Aronson, and I think this is a really nice way of explaining it. So if I had to say in one slide what is the best slide for saying quantum theory, well, like probability theory, which you all know there's a transfer matrix that takes a probability to a new probability. In quantum, there's a unitary that takes an amplitude vector to a new amplitude vector, but what's different is this amplitude vector can have positive and negative numbers. So it can have the ability that these two negative numbers can add together to give 0. It can give interference. And it's this interference that is the key that we have to exploit to do quantum operations. And this is a real gross oversimplification of what an algorithm is, but you can think of an algorithm as this as 3 main steps. The first step is to get your system in this quantum superposition of all states, and you do this by applying your Hadamard gates. The second step is to come in and encode the problem through a series of gates into the quantum computer by changing the phases and all this. And then the last step is to use interference and compress this to a small number of outcomes that you can easily sample. You may have to repeat the encoding and the compression many times, but as I said, this is an oversimplification of quantum algorithms, and this talk is not about quantum algorithms. And those that are interested, I'd suggest go read the lecture notes by Andrew Charles and many others, or even do an ACM just on quantum algorithms, because there's a lot more detail. But to get to what I want to talk about, you probably heard there's a lot of excitement and there's a lot of things that we know about quantum computing, but generally that's in this regime that we call universal fault tolerant. What this means is I like to think there's three types of quantum computers. The first type is this universal, and this universal is one where we know that there are algorithms that are better than the best known classical algorithms, but it requires error correction. And at the moment, we haven't demonstrated error correction. And the overhead for error correction using our systems or other systems is quite large. And so this is still probably many years away. The other type is what I, down the bottom, like I like to call analog or quantum annealing. And this is trying to make a system to emulate another system. I don't think this is that programmable, and it's hard to understand what that does. And what's emerging now, and what the goal of what we want to do, is the middle one, which is approximate quantum computing. And this is a quantum device which doesn't have fault tolerance, but we aim to work out and understand some useful application or demonstration that allows us to compare this to classical computing. And if I was to put this on a timeline plot, I would say we've been in this blue zone where we've done a lot of key demonstrations, and we're entering this green zone. In this green zone, we want to get to this gray zone, which is universal fault tolerance. But to get there, we've got to build the tools that allow us to understand how to get to universality. So we've got to build the tools that allow us to understand these near-term devices, how to control them in the order of 1,000 qubits with circuit depths, which is how many operations of, let's say, 1,000 and beyond. And when we put this down, we can outline what our technical goals for QISKit is. And basically, just reading off this slide, they're to continue the improvement of quantum devices. How do we increase the size, capacity, and fidelity of these operations? How do we build the software and tools for working with these? How do we come up with investigating short depth circuits to look for where we have quantum advantage, which is sometimes compared to classic, like where quantum is better than classical? And how do we learn about these devices of how we will implement fault tolerance in them as we go along this path of making the devices better? So we want to create this framework where we can study experiments and simulations and analyzation tools that is backward independent. It has multiple different types of simulators and analyzation tools that we build in, and it allows us to automate a lot of the rewriting so we don't have to do it by hand, doing the optimization, like reducing the gates to the fundamental ones that are needed, how to do the scheduling, and ultimately how to map it to the different hardwares. So we've put something in place. Over time, we're going to add more features. We're going to go lower, going lower to give users that really want to get into the nitty-gritty some understanding of exactly how the pulses and pulse timing works. And at the same time, for the users that even find the quantum gates a little bit too low level, how do we abstract this to higher level abstractions to allow different types of people to explore in the higher space? So this is the goals. This is basically the goals for our QISKit platform. So let's first go through some backends. So the IBM Quantum Experience is a set of devices and online simulators that we have made available to the public. In particular, here's a quick anatomy of our devices. They're superconducting qubits, which are basically the qubit lives in a superconducting oscillator. For the details of that, it's not so important, but you can think of these as tiny little oscillators that are little voltages that are oscillating backwards and forwards across. In this green highlight here, you'll see two pads. Not having a mouse pointer is hard to do it, but they're little oscillators oscillating about 5 gigahertz. We then connect them with waveguides that represent the either the buses or readout. So going into the zoom in of this superconducting, you can think of the qubit as basically being this little oscillator in the top left-hand corner. We have qubit pairs that either exist on the top or bottom, and they oscillate backwards and forwards across this junction. And this junction is anemonic enough that the two lowest levels can be separated, and these become our qubits. We call them, if they're oscillating in the 0 state, the ground state, oscillating in the next excited state, the 1 state. The way we interact them is through this thing that we call a bus. A bus is just some way of coming up with a photon that allows us to exchange, a microwave photon that allows us to exchange quantum information between different qubits. So this bus mediates an interaction between the two qubits. So in this picture here is a picture of a 16-qubit device. The square pockets are the different qubits, and then this is connected in this ladder arrangement, where the buses are connecting Q1 to Q0, Q1 to Q2, Q2 to Q15, and so on across. And you can think of these are all the places where we can do the 2-qubit gates. So the current devices that you guys can go access, sorry, the slide is a bit messed up. The current devices that you guys can go access consist of, there's a 5-qubit device, which has typical coherence times of 50 microseconds. You can think of this as how long the quantumness stays in our system. It has single qubit fidelities, which you can think of how well you do the single qubit gates of about 99%. It has 2-qubit fidelities, which is the same for the 2-qubit, of 95, measurement fidelities of 93, and the arrangement is given by these cartoon pictures where the arrow indicates the gates. So you can do a gate between 4 and 2, 3 and 4, 3 and 2, and so on for this 5-qubit device, and the same for the 16-qubit device. So you can think of that as the direction that specifies the control operation. And the 5-qubit, we give a graphical interface that I'm not going to go into in much detail in this for people that really want a quick view and quick understanding of quantum computing. And the 16-qubit is where we enable through the QISKit, which I'll explain a lot more. But before we go there, we also have a lot of other, you can see all our backends that are available. So if you go to the Quantum Experience and go to the Device tab, you'll see a list of different devices that are usable. At the moment, we have 2 5-qubits that are online, a 16-qubit, a 20-qubit for clients, and we have 2 simulators. We have a 32-qubit simulator that works when you don't want to put in classical conditionals, and a 20-qubit simulator if you want to put in classical processing. Okay, so you can find all the devices we have available, and we will be making more and putting towards sort of a HPC and a device platform. For those that want more information, we also provide a GitHub description of the backends that tell you about the list of people that made this possible. It tells you some more information about the performance of the devices, how we measured them, how some types of known errors we know on them. It also tells you how those gates, which you're going to implement, are rewritten in terms of pulses that are sent to the system for the person that knows a bit more about the physics of the system. So it gives you a description of how we think this backend is performing and gives you the information that you may need to understand why it's not performing the way you expect. And the one plug I will give to the Quantum Experience before I move on to QISKit is there's a lot more there. There's a community of over 60,000 users. There's a forum where you can ask questions. There's a video where you can get a video description of little key topics, papers from both the IBM group and external people using our devices are collected under the papers. And we're just going to announce starting very soon awards, but you can see what those awards are, where people can look at them, and there's a best paper award, best tutorial award, best solution for a programming challenge. And just if you're interested, we're going to try and award the community that want to try and add to our stuff. And there is, as I said, for the real beginner, if you want the graphical interface, there's a graphical interface that allows you to control 5 qubits. So getting on to the core of what I wanted to talk about. So we need to come up with a way that we can define an intermediate representation. So some representation that is like the assembly language for classical computing. And QASM has been around for a while. What we've done is extended it under what we call the OpenQASM, and I'll just describe a bit of that. As I said, a quantum circuit doesn't tell you timing explicitly, but it tells you dependencies. And it tells you a way, and what we tried to do is a way of separating quantum and classical processing. For those that are interested, we have a white paper describing in details a lot of it, and I'll go through it in a second, a highlight of it. But you see here, this script is equivalent to this picture that I've been showing. So you have part of it where, you include some functionalities that I'll go through. You have a part where you declare your qubits, a sequence of operations, and measurement, and some classical computing. So to go through the different types of parts, there's the declaring the quantum and classical registers. So these are the registers that will either be processing the quantum and classical information. There's the set of gates that you'll build other gates up through using subroutines. And as I said at the start, universality can be done between a C0 and an arbitrary single qubit gate. So from these U and CX, we can build up the other types of gates which we enable through subroutines. We've allowed an include where it includes many of the standard gates. You can perform register level operations. So rather than writing a Hadamard on qubit 1, a Hadamard on qubit 2, you can just perform a Hadamard to all the qubits. You can measure qubits, and this is the part where you do some measurement on the qubit and you take the quantum information and assign it to a classical information. There's the part next where we allow you to insert barriers. As I said, we're not putting timing into this representation out of choice, but we want to be able to give the user the ability to make sure following optimizations do not optimize the circuit over barriers that might be of interest for the user. So you're doing a series of circuits and you want half the circuit always to prepare the same preamble. You may not want that to be optimized with the later part of the circuit. So barriers act as a way of making sure that later forms of optimization are not optimized across them. And then finally, there's classical conditional operations. So once you've turned this classical quantum information into classical information, you may want to do future quantum operations that depend on the classical registers. And we do this through if operations. Okay. So the API, as I said, we want to make these backends usable by people. So the first thing we want to put in place is an API. The API part of the QISKit is a way that you, in some language of your choice, can find information about the backends and submit these QASM circuits, and then retrieve the results, process them, come back later, look at different types of problems, and we do this through authentication using this token. We have description on it, but basically we make sure that a user, you can get back the circuits you want. So to give an example of how it works, in Python, you import this, you have to set up your token, which, as I said, describes a different type of user and the website, the web address for that backend, which is the Quantum Experience. And you set up this API, and this is what's done in the first part of the circuit. And then if you were to go there and get all the available backends, you see when this was run in Python, you see at the time there's the IBM QX4, the IBM QX5, the IBM QXQASM simulator. These were three types of online backends that would be available to the user. Actually, this slide needs to be rerun and updated because we've just added a few more online simulators, and so there would be a couple more listed in there. Then if you want to get extra information about this backend, you can get that by just getting, like calling the information. You find out what gates it supports. And here, this one supports the single qubit rotations in the C0. It tells you the coupling map, which is the graph represented for the connectivity of the qubit, a simple description, an ID for it, and how many qubits it's used. So if you wanted to use this, you can submit a job. So if you know your QASM and you've got this text file saved somewhere or this QASM file saved somewhere, you can load it, you can run that job, Using the backend, the IBM QX4 in this case, you can describe how many shots, and then you'll get back your information that will tell you it's run. You can check the status using get job status, and when it's done, you can get the results. And in this particular case is rerunning that Bell experiment that I described at the start, which was performing a Hadamard on, well, actually here it's slightly different because the connectivity wouldn't allow the C0 to go from 0 to 1. So we're performing the Hadamard first on qubit 1 and then the C0 from 1 to 0. But you get, as expected, you find that the number of shots gives you most of the correlation in the 0, 0, very little in the 0, 1, 1, 0, and 50% in the 1, 1. So as expected, 0, 0, and 1, 1 appear with similar probabilities close to a half. Okay. This is well and good, but it's not easy if you want to work with many qubits. It's not easy, as you saw in that example, you had to write your circuit exactly for that back end and exploit the gates that it was. So if you want to do more complex things, you need to start to work to an SDK. And this is what we're putting in process, and we've done through the SDK part of QISKit. So just let me grab a drink of water. So the QISKit SDK. So we're using open development process as already stated, and you can see it on Git. We have documentation. Like all projects, I would say the documentation needs a lot of work, but we're committed to improving that. But there's documentation that tells you how to get started and how to use it. So I recommend after this, if you're interested, go looking at the documentation. As I said, we are mainly doing our first one in Python, but we're also committed and we started making a Swift and JavaScript version of the SDK. So depending on the language that you would like to use, we want to enable working with our systems in as many different types of languages as possible. So let me go through exactly how you are. So the goal of the SDK, as I said before, is really to enable research and further development of these applications in near-term devices. So it consists of basically three parts. It consists of a quantum program part, which I'll describe in the next few slides, a transpiler part, which I'll describe, which maps circuits to other circuits, and different backends, which I've already described. So typically what you do is you go through this process where you initialize your quantum program. So this is defining the whole thing you want to do. The first step is then you define in this quantum program what are your classical and quantum registers you're going to use. And this you do by declaring some quantum registers. Next, you want to build your circuits. So we've got to give you the tools to allow you to build many circuits. So that goes through a building circuit. Then you want to look at different backends that are available, whether it's simulator or real hardware, and you want to say, can my circuit be run on that hardware? And if so, you're going to map it to that hardware. Then you want to execute it, analyze your results, and continue this. Okay, so the first part is we allow you to pip install QISKit using the standard Python, so you can just install it. First part is just to import your QISKit, set up your API tokens, your URL as we described before, and import the quantum program part of the package. Now, the main part of QISKit is this quantum program. You can think at the moment of the quantum program as a collection of quantum circuits and methods of what you want to do with the current experiment. It's a place to build and store these quantum circuits and work with them and run the experiments. Actually, it's something we're internally trying to see whether or not that definition can continue, but in our current version, think of it as just this method of a collection of quantum circuits and methods of what you want to do with them. So the first part of when you work with this is create your quantum program. Then you want to come in and you do that with a simple command in Python of those that use Python of initiating quantum program object and assigning it here to some variable we call QP. Then we can add to this quantum program the different registers. Here we've added a quantum register of size 2, and we've added a classical register of size 2. So now we've got a program, and we've got assigned to that program both a quantum and classical register. Now you go to the stage of wanting to build your circuits. So in the first 4 lines are just repeated from the previous slide. The next part is you want to create a circuit on those registers. So we create a circuit which we call Bell on the quantum register and the classical register, that using input line 5 on this slide. And then you want to start adding these operations. Now, because here in this, we're not limited by the actual hardware behind, we're going to start and make this the same way we did at the start of this talk and perform the Hadamard on Q0 and then perform the C0 between 0 and 1. So we go to our Bell circuit, we add a Hadamard on Q0 with the input line 6, and then the next step is we add the C0 between 0 and 1 with the input line on line 7. And then just because we may want to separate for now measurement and Bell, we make a new quantum circuit that we call measurement, and now we assign that as an empty quantum circuit on the same registers, QR and CR, and now we add the measurement that measures the full register QR into the classical register CR. So that's going to represent here measuring qubit 0 to classical bit 0, qubit 1 to classical bit 1. Okay. So all the different back ends, I can't really tell, but on my internal slides, the fonts got messed up. But what are the different gates that you have? You have a bunch of single qubit gates. You have anything that if you've used the Quantum Experience, those ones are being added. These represent the X. The X is the bit flip. The Hadamard represents a superposition gate. Then all these S's and T's are different types of phase gates. They have other single qubit gates, other rotation gates. You have various different 2-qubit gates. You have a lot of the standard types of gates that you'll find in textbooks that we've made as available extensions that can be added. Then we've also added some unique additional circuit construction methods, and these are if I want to perform the inverse. We give you a gate that you know what the gate is, and you can perform the inverse of simply adding the inverse to it. And finally, if you want to condition that gate on classical information, we give you an additional control with this construction method for making a conditional gate. So these are all the different types of things that we've given at the moment, and we're making it extensible. And we give you a way of getting the information back. So for instance, in the circuit that we just made before, we had the 2 circuits, Bell and measurement Z. We can get the names back with a simple get circuits names command. We can get the registers if we wanted to check the registers with a get classical register, get quantum register names. And if we wanted to see the 2 QASMs that we've made so far, we can get the QASMs through the get QASM, and you see on the first one, you have the creation of the quantum registers, you have the Hadamard gate and the CX gate. On the second one, you just have the measurement. Okay. Now, as I said, once you've made one type of measurement, a lot of times what you want to do is add a bunch of circuits together where the first part is represented, the first part is constant and not changed. So if you wanted to do this, repeat this example I gave at the start and measure in the X basis, you would make the measurement on the quantum register in the X basis by first applying a bunch of Hadamards, which we do on input line 11, and then we would assign those outcomes from the quantum register to the classical register, which we do on line 12. So now we've got a new quantum circuit that represents measure X, and now we give the ability that you can add these 2 quantum circuits together. So we can make new circuits, which is the Bell and the measurement Z basis, which we do by simply going Bell plus measurement Z. And what this does is it just takes the quantum circuit for the first part and appends to it the second part. And then we can make a new circuit, Bell measure X, we do Bell, and then we do measurement in the X. So now we have those 2 quantum circuits for the entanglement example. If we start and ask through the quantum program the different available backends, we find if we haven't enabled the API, we just have the local simulators. We have a local C++ simulator, a QASM simulator, and a unitary simulator. But if you enable the API, then you'll see the online simulators come available, the hardware comes available, and you get available a lot more backends. If you just want to look and see the online ones only, you can just look at this with an online backends command. So now you can find the backends which you have, which you can use, and now we can start to run the circuit. So the first part, as I said, is you may want to check that your circuit can run on that back end. So one of the things you have to do is get the configuration. So on line 16, we check the back end to find the direction of the gates that are available. And we do this through this coupling map. So here it allows us to determine from the configuration, we grab from the dictionary the coupling map and assign it to this parameter I call CMAP. And now we can execute the circuits that we want to execute, the bell in the measurement Z basis, the bell in the measurement X basis, on this back end, IBM QX4, which is one of our 5-qubit devices, using the coupling map from that back end and specifying the number of shots that we want to run. And what we find is very much like I showed with the graphical interface at the start. We find that of that 1,000, almost 50% of them are in the 0, 0 and the 1, 1 when we measure in the Z basis. And then when we measure in the X basis, it's also in the 0, 0 and 1, 1. So either with you're in asking, if qubit 1 is in 0, the other one is in 0. If qubit 1 is in 1, the other one is in 1. If qubit 1 is in the plus state, the other one's in the plus state. If qubit 1 is in the minus state, the other one's in the minus state. And this is a hallmark of the entanglement that I mentioned at the start. Okay, so what is happening? Well, as I said, the circuit doesn't support the gates that are allowed. For instance, in this IBM QX backend 4, the C0 does not go from 0 to 1. It goes from 1 to 0. So what happens in the circuit is we have to rewrite the circuit. So when we rewrite the circuit, we take in this Hadamard operation on Q0, followed by a CX from 0 to 1, and we rewrite it in terms of a new operation and the C0 that is actually allowed. Okay, so this is the goals of the transpiler part of QISKit. So basically, what happens is, and I will admit this is the part that we are actively working on to make more modular for our next update to allow it easier to see. But behind the scenes, what happens first is we unroll all of the gates into the single qubit gates that can be run on the system. Next, we go through and make sure that we change the directions of the C0s by inserting swaps into the directions that are allowed in our experiment. Then we minimize the amount of C0s, we optimize the single qubits, and this forms the first part of the different passes of the transpiling to get it. One thing I definitely want to work on is making this modular so that users can suggest different types of transpilers, different types of backends, and this is one of the things we're working on. Okay, often you may want to also get a simulator. So if you wanted to know what the quantum state is, we give the option that you can look at the backend, use a backend, which is your simulator, and if you're using the simulator, you can get the extra information that represents the quantum state. And so in here, for instance, we execute the same circuit, and now we get an array that represents the quantum state. As with all exponentials, as I put more qubits in this array will get really big, and so you're not going to do too many qubits. Sometimes you also want to get the unitary that represents that quantum circuit, so that full matrix. If you use the unitary simulator, you can get the data and it will return the unitary that represent it. So these are, you think of checks to ask what's going on and help you debug. We've also added a lot of visualization tools. And if you want to visualize quantum states, we've given you an option that you can visualize it in your favorite method of visualizing. There's this method here is known as the city method. Basically, it represents the quantum amplitudes the outer product of the quantum state. So 0 here is the Bell state. You see that there's an amplitude connecting 0, 0 to 0, 0, 0, 0, 0, 0 to 1, 1, and the same for the 1 states. So this represents one type of view. There's different types of views that can represent a quantum state. How you best visualize a quantum state, honestly, is a question that scientists are still discussing. And we've put a few in there, but they give you some way of understanding what's going on. Now, why do we want to give you this ability to send many circuits? Is like many of the things that you want to do with these devices is run a batch of things to ask certain questions about the device, either for verification or to do some type of quantum operation. So if I wanted to actually make that quantum state experimentally, I would have to run many different experiments. So, and each one of them would give me a different matrix element or a different part of that quantum state that I would have to put together. So this is known as quantum state tomography. We've put tools in place that allow you to do this, and this is one of the examples. So the first step is you can import the quantum tomography tools through the QCVV tomography packages, and now you can build all the circuits to allow you to do quantum state tomography. So you give it the Bell state, and then you say, I want to build it on the qubits I want to measure, for the registers I want to measure, and build it all into that quantum program. It's going to build the 9 different circuits that you need to run to reconstruct this state. It's then going to, here it's executed on the simulator, but it's going to execute those circuits and give you the 9 different histogram outcomes from those circuits. And that data is going to represent the shots associated with the different labels for all the different 9 experiments. And then we've provided tools where you can put them together and reconstruct them into the quantum state and represent and then replot it, reconstructing it from the raw measurements. So this gives you a way to automate the task of doing quantum process tomography. Lastly and quickly, as we get a better understanding of what we're going to do with these near-term devices, one of the most promising algorithms is the VQE algorithm. Still, a lot is unproven by this algorithm, to be honest. But it is a way that we can explore solving the eigenvalue equation on a quantum computer. How it scales and what is its limitations is still open research. And basically, think of it a way as trying to prepare the eigenstate to some Hamiltonian on a quantum computer, and then asking the quantum computer to estimate their eigenvalues, and we use a classical computer to change the amount of controls as we try and find a better answers to this question. And if we can change the controls in a way that we get closer to the answer, we know that if we get to the minimum, we should get close to the real answer. And this eigenvalue problem turns out to be one of the problems in understanding some of the mapping out some of the energies for quantum chemistry. So there's an example of showing that. So here's an complete description, but essentially you have some chemical Hamiltonian in some basis that you want to map to something you can represent on a quantum computer. You then want to come up with some creative choice of the trial function, which I show in this equation down the bottom. And here it's going to be an iterative series of entangling operations and the single qubit operations of some depth m, and we're going to apply it on the plus state. Then we want to estimate the energy. So we generate that trial function, we generate a term, we estimate the energy for that trial function, then we go to the next term in the Hamiltonian, we keep adding them through. Then we change our set of thetas to get the next term, and so on, and we iterate iteratively, doing this sort of hybrid interaction between this classical and quantum. And what you can see as an example in that notebook, if we take an exact point, this top graph shows the number of trials for a given energy, given point. So we've got some point, we start, and our ansatz is particularly not close to the optimal, and we then go through and choose the next trial. we run it, choose the next trial, and so forth, you see it converging to exactly what we know as the final. So it's following a standard type of optimization problem. Then we can map out this full contour of hydrogen. And this is better described actually on the next slide. So we can do this experimentally as well as with the notebook. So here is this contour of hydrogen, and we have some Hamiltonian that represents the problem at one distance, where it's at the minimum. We have one distance where the hydrogens are dissociated very far apart. And we know the solution classically. The classical solution for this problem is easily as term. But we can go through and we can apply this bunch of quantum circuits to this ansatz, and we can minimize it. We can map out the first answer, the next answer, and so on. So this shows a way of using a quantum computer to look at some problem of interest that allows us to explore through the tools that we're putting in place with QISKit. So what have we done? We've put a lot of tools in place. We have a lot of tools for visualization, some tools for the chemistry problem. There's also an optimization problem in there. We've put a lot of tools for verification and for validation, which is trying to understand how a system is quantum. And we've made tutorials explaining this to explain how it works. And I think I'm just going to conclude by saying if you want to explore, go to the QuizKit.org and explore. If you want to contribute and help build the code, go to the GitHub. And if you want to help define where we go to the Slack channel and discuss with the team. Thanks.
Well, thank you very much, Jay. That was a great presentation. So we have some time left here. Jay and I are both willing to go over, but we have about 4 minutes. We're going to probably extend that maybe a lot longer since we do have a number of questions. And Jay, I've kind of broken these questions down into a few areas. There's some general quantum-related questions. There's some IBM Q related questions. And of course, there's some QuizKit-related questions. Probably want to focus pretty heavy on those. But let me ask you a couple of the general questions and get your opinions. You know, one of the questions I saw that was very interesting was, what is your take on the quantum advantage, you know, being achieved at 50 qubits, or what number of qubits, what factors do you think come into play with actually getting to a quantum advantage?
Yeah, so I think more important than the number of qubits is actually the depth of the quantum circuit. 50 qubits or 100 qubits that don't interact is not that difficult to make. Getting them to interact with high fidelity and really exploit the full space, that becomes difficult. So it comes down to some combination of the depth of the quantum circuit and the width. Because I made this talk focused on QuizKit, I didn't focus on some of the other work we do. And in particular, we like this definition we call the quantum volume. And this represents some amount of computational space that I'm using in my circuit. So how many gates I've done, but if you can think of it loosely, is the number of gates I've done times the depth. I don't think it's a hard limit. Because it's exponential, we'll know when we're past it. As we get close to that limit, people will find tricks for certain types of circuits and show you how to do it. But one of the things that we don't exactly know is how noise comes in and influences us in working at it. So if I had to give a number, I'd say by the time we hit 100 to 200, we're not going to be able to simulate it. When we hit 50, it's definitely going to be interesting, but I'm more focused on understanding how good our 50 or how good our devices are.
And so that leads, you know, one of the other questions was, what are the difficulties faced today in adding an extra qubit? And I think you kind of answered that as well, which is not necessarily difficult to add qubits, far more difficult to get them to interact together and actually do some demonstrable function that has an advantage.
Yeah.
You know, one of the other questions in the general quantum area was, do you see quantum computers as standalone platforms or merely as coprocessors for classical host processors?
So in the near term, in the sort of approximate quantum computing, it is not going to be standalone. Why we don't have error correction and fault tolerance, it's going to be some type of thing that we're going to run a circuit, sample from it, put those numbers together to estimate either some Hamiltonian or some sampling problem. And it's going to be some type of like extra thing that we attach to it. exploring and like one of the things which I probably rushed over is it's important to separate what we can do with fault tolerant, so error-free qubits, and what we can do with short depth circuits. And what we can do with short depth circuits is still exploratory, but it's also fun because it's new. So for the short depth circuits, I think it was going to be something we add into the classical architecture.
Very cool, very cool. And so, you mentioned, things like fidelity in your presentation. What do you think fidelity needs to be is one of the questions to consider a quantum computer actually usable as far as the results. Fidelity and error correction, something we talk about all the time in the space. Where do you think we need to get with that for things to actually become, what this user asks is more usable, but, kind of something everyone can use? It could bring us closer to a general quantum computer.
I think people can already use it now. But I agree that since I can simulate and predict it at these numbers, it's probably not like my laptop's going to do it. But I don't think it's a hard threshold. So there are thresholds for error correcting codes to go. I'm excited by asking the question, and I think the creativity of the people will find better ways to do this. If I can trade some resources, some numbers of qubits, and do some form of error correction, or I like the term error mitigation, then I think you're asking, how do I get creative to explore the best I can do out of a device? If I can come up with ideas that I can push some of the errors to parts of the processor I don't care about, I can extend the depth. So I think you're going to see a lot of creativity in working out how to best get things out of it, which eventually will evolve towards doing error correction with the devices, but it's not going to be a hard line. I think right now you can start doing things, and I'm very excited by understanding not necessarily new like going through and doing more chemistry, but are there ways we can make the end result better by coming up with error mitigated techniques?
So, that really is a great lead into, a more related to the IBM Q project. What does IBM see as some of the near-term applications to run on some of these things that you're building and things like QISKit?
The near-term applications, the chemistry is a good example because we know chemistry is hard. We know that representing the solution is hard for a classical computer to do. So I would argue chemistry is the most developed. Internally, we're also, like everyone else, we're interested in understanding how quantum influences fields of machine learning, AI, and things like that. But it's going to be things that exploit linear algebra and you can exploit this growing space fast. And because a quantum computer applies linear operations. So I like chemistry. I like looking at AI. I think, and the other side is understanding how to use ideas from error correction to make the devices perform better.
That's awesome. So, one of the things that was asked in a couple different ways, and I'll kind of take those questions and summarize them. And the one was, why, from a programmatic standpoint, why does IBM feel the methods that they're using are the best approach? A couple of users asked if we're using JavaScript and Python and things like that that are conventional computing languages. Is that really the best approach? Should there be a quantum computing language, or is it best to be using these things that developers already know and have access to? Many systems use the Python, so I think that's kind of become a default as it has in machine learning, right, if you go look at libraries. But what's your opinion on the use of those languages versus a dedicated quantum computing language or something that might be a different approach?
Yeah, this is a really good question. So I think when we have fault tolerance and we're doing things there, then that will be a different way of, like in that slide where I had the slide of the number of qubits versus the number of gates. we want to get to fault tolerance. And in fault tolerance, you can start to develop high-level tools and routines. Understanding how you best use these near-term devices, you don't want to develop too much of what we've already developed before. So if we've got a language that allows us to do a lot of the classical functions that we need to do, we want to exploit that. And since we're at this point of exploring what I like to call approximate quantum computing, or quantum computing without error correction, where things may change as I learn. One of the big differences, if I'm doing fault tolerance, I have a finite set of gates that I use, and then I come up with tools that map it down to that finite set of gates. And in fault tolerance, one of the gates that is actually very hard to do is this T gate, which is actually a single qubit gate. With real-term devices, if I want to do this T gate, which is a single qubit phase gate, it's actually very simple to do, but I don't do it error-free, right? So the goals of where we are now are different to where we will be when we know how we will do error correction with these devices. So whilst we're in this part of learning about the devices, developing the tools to best exploit them, I don't want to rewrite too much of what we've already done classically, but append to it quantum assembly, or append to it quantum operations, and allow us to quickly explore and work out what are the best paths. And then as we learn, we adapt.
That's fantastic. Well, so in the few minutes we have left, let's jump into some specific QuizKit related questions. One of the first, which is I'm actually embarrassed to say I never even looked or know, is what open source license is it using? I mean, Jay, is that the IBM public license version, or what license is this actually under?
Apache.
It's under Apache license. Is that Apache 2?
Yes.
Oh, great. All right, so one of the questions I thought that was really interesting is somebody asked if you could do a compare and contrast. What are the similarities and differences between what you're doing with QuizKit and some of the other things, Liqui, and things that are out there? Maybe you could give us a little insight into either difference in approach or perhaps, advantages that users might get by using QuizKit.
Yeah, so one of the things that QuizKit is focused on is enabling users to get the most of real hardware. So we are focused on giving the tools that try to give you the information about the real hardware, what you need to know, and how to best work with that hardware. So I think it's just a definition of scope. Others are scoping for different, they are different areas. We're scoping to work with the hardware, and over time we're gonna keep I like to think of it as 3 user bases, and there's probably more. I like to think there's this physics developer basis, which is I want to know the pulses and I want to know exactly the hardware. They want to get in, they want to do pulses, right? They need to know timing and controls like that. So that's like someone that's getting in there, doing the pulses, lining up the timings, but that's very hard to build and compile. It's some type of machine code or someone that's interested in changing that. Then there's the quantum circuits, and that's almost like writing some type of quantum version of assembly language. And then there'll be a third API that'll be some type of higher level interaction. And to start with, we chose the middle one, and we're going to, as I said, try and work out how we go into both spaces. But we're putting a real focus on trying to make sure that you can work with the hardware that we provide and automate the tools needed to work out the next steps.
Very cool.
I don't really want to go too much into the different, that's
totally.
our goal.
That makes a lot of sense. Well, look, for the last question, I thought one of the really interesting ones that it came up a couple of times during your presentation is, can you tell us what the Hello World program of quantum computing is? Like, for the people who are on here looking at QuizKit, they go and they download it today. They look back over your presentation. They're going to run that first thing. What is the equivalent Hello World for them?
Yeah, so I actually tweeted this a few months ago. I think this is a good question that we need to decide. So obviously in my presentation, I focused on the ability to make entanglement. I think that is one good candidate. Another good candidate is teleportation. Teleportation is a little bit harder with real devices because that requires getting the classical feedback and things like that working. We enable that only through simulation at the moment. So one of the users of QISKit is James Wooten. He likes to present games, so to give users a little bit of feel for something visual in return. And entanglement doesn't have that feel of a visual return. So I kind of like what he's saying. I don't know if I fully think we know exactly what the hello world is, but it feels like it's got to be something that returns something to a screen that is like some form of like a bit more like some type of human sort of feel. Like it prints to my screen hello, right, when I run it on a classical computer.
Right.
I think entanglement is a little bit too, like, it's kind of showing the outcome of a couple of NOT gates. So I think I agree with him, we need some type of visualization or some type of game. And I think we're not there yet. I would say for those users, they got to get in there and explore a bit of the details of how it works. But I'd like to continue this conversation because I think it's a good conversation to work what is the best hello world.
Very cool. Well, I'm afraid we've run out of time today. Jay, I'd like to thank you for your informative presentation and the insightful answers to the questions. And a special thanks to everyone that attended for taking the time to participate in today's webinar. The webinar was recorded, and it will be available online in a few days at webinar.acm.org. You can find the announcements on upcoming webinars and other ACM activities at learning.acm.org or at acm.org. Also, please fill out a quick survey where we can suggest future topics, speakers, anything that you'd like to see. You should see that survey on your screen right now. We would really sincerely appreciate the feedback so that we can improve these moving forward. On behalf of ACM, Jay Gambetta, and myself, Worley, thanks again for joining us, and I hope you all join us again in the future. This concludes today's webinar.